talked about interference filters. Remember what interference filters, we talked about the dielectric layer. Dielectric layer is between two metallic films. Remember, while we are talking about filters, what do filters do? We use prisms and what? And filters. So what do filters do? Our understanding is based on knowing what filters do. Filters, by their very nature, they are going to select some wavelength of light. But how does that happen? How do they filter that? So once the radiation strikes the filter, so notice here we have a glass plate, we have white radiation here, all the light is there, the white radiation. And then we need to choose a wavelength for our analysis. So we need a glass plate here, and much more important is the dielectric layer. That is going to be important. Then the dielectric layer is between two metal films. You can see there, two metal films here in a black color here. And what you see emerging on this other side of the glass plate is a narrow band of radiation. So here you start with white radiation, all wavelengths of light, but you need to select some light. And I want to impress upon you on what the differences are in the interference filters and how they work. So our understanding on how they work is based on this diagram here, all right? Then everything makes sense. So white radiation, and emerging from the glass plate on the other end is a narrow band of radiation. So the radiation strikes the filter, and some will be reflected by that glass plate, some will be transmitted, and the transmitted light will reflect off the bottom surface. But before it reflects off, you can see it goes through the dielectric layer. Dielectric layers, by their very nature, are good insulators, but they are capable of storing charge, all right? So that's what a dielectric layer is. So the light is then transmitted, it's reflected off the bottom surface. So you see, that's where you have the light coming off. If there is the proper radiation lambda, wavelength lambda, if that light that is reflected is in phase with the incoming radiation, there will be, if they are in phase, the other wavelength of light will undergo destructive interference. If they are not in phase, if they are in phase, they will undergo constructive interference, all right? So here, on this second diagram here, you would see parallel light here. It strikes the surface A, that's a crystallographic plane A, and then it can be reflected to one. You draw a normal, you normally draw a normal to the surface. And then you have theta, that is the angle there, and then that is theta as well. Then that is the first plane is labeled 1. All right? And then we have the second plane is A and B there. And then if that light, that ray of light goes through, it's 1, then it's reflected, it's 1 prime. So if there is constructive interference, then you choose the wavelengths of interest for your analysis. So that if that is the case, if the wavelengths are in phase, then the transmitted wavelength, the transmitted light through the filter will not be, if there is constructive interference, okay? If there is destructive interference, it is like that light is destroyed. And so we are going to say that's the blocked by the filter if that light or that wavelength of light is destroyed. We can view that as a destruction by the filter. All right. Do you have any questions so far on this particular diagram? So having understood this, then let's move forward. You can choose the narrow range of lambdas that are transmitted based on your dielectric layer. So that is what you would choose, all right? You will choose the wavelengths that you will be interested in just based on the dielectric layer, all right? Let's give some further information here, and then you would see how this is going to be useful. First, you notice the same diagram we have. We have the distance between the two, the dielectric layer. Dielectric layer, you have D is the thickness of the dielectric layer, this distance here, that distance. And then you have N is the order of interference. Order means 1, 2, 3, 4. That's an integer. Starts with 0 of 0 order, of order 1, order 2, order 3, and so forth. And we have lambda is the wavelength in the dielectric. Lambda. Then lambda prime is the wavelength in air. Wavelength in air. So there's lambda, wavelength in the dielectric, lambda prime, the wavelength in air. And then there is neither here, this sign here, is the reflective index of the dielectric. Okay. Now, having said this, without going through all the math, we have n lambda prime. If you go through the math, so calculus. N lambda prime, n is the order. Remember, it can be 1, 2, 3, 4, and so on. And then you see lambda prime is the wavelength in air. So n lambda prime is equal to 2d over cosine theta. That slash is over, all right? So remember, when theta approaches 0, remember the cosine of 0 is 1. The cosine of 0 is 1. So when lambda approaches 0, the cosine of theta is 1, which means, remember, theta is what again? That angle drawn to the normal. Okay, if that is 0, then you have this unique equation here, n lambda prime is equal to 2d. And so then there is an equation that we give you, it's derived and say they tell you, oh, and so they give you this equation in the textbook, they try to guide you. And so here, there is an equation that correlates a relationship between lambda and lambda prime. Remember, lambda prime is the wavelength in air. And when it comes to that material, the dielectric, then it's going to be bent or reflected, hence the term reflection. So reflectance filters, okay? First it goes through the filter. So you have this lambda is equal to 2dn over, those are two n's here. You have to be aware, those are two different n's. What does the first n stand for there? Okay. So you want to be sure to define those two terms. Okay. So the N, the top point, remember this is dN. dN is the regular whatever ddt, whatever that change the wavelength. That's what that dN is. We together there. And then the bottom one, okay, the bottom one is the normal order of interference. So dN over N, the change in the orders there. So again, so this equation is going to be important. So here then, again, going through what I've said, it's the same thing here. I just want to be very clear on what these waves that you are seeing here. It's really, you can see the arrows that's reflected back, or it's going to be bent or go through. You can see that, right? If it goes through the glass, it can be reflected back and then it's bent, all right? So it's at point one. If you see this point here, there is this wave here, or this wavelength. The radiation is partially reflected and partially transmitted to point 1 prime. So there is partial reflection, and some of it will be partially transmitted to point 1, where the partial reflection and transmission again can take place. So you have all these orders of reflection. So if you have many, if the material has many layers, you can think of it as orders of reflection associated with crystallographic layers. And then the same process can occur for 2. It can be partially reflected, and then it can go to point number 2 prime. For reinforcement to occur at point number 2, notice here, there is this partial reflection, this dashed line. Then when it goes to 1 prime, it can also be partially reflected. For reinforcement to occur at point 2, the distance traveled by the beam reflected at 1 must be some multiple of its wavelength in the medium lambda prime. So it must be multiples as it's found. And because the path length between the surfaces can be expressed as d cos theta, we have written an equation to solve that equation, all right? What was the equation again? What's the equation again?
Wavelength equals 2dN over N.
Yes. What about the one relating the cosine?
2d divided by cosine.
That gives you lambda.
Yeah.
Lambda.
No, that gives you n lambda.
2d. So you're saying there, n lambda prime is equal to 2d cosine theta. So it's important to have that equation in mind. N lambda prime equals to 2d cosine theta. And this is what is explained here, and you can see the reflections. So it tells you from 1 to 1, I've abbreviated it to t over cosine theta, where t will be 2d. See that? So it's the same thing that we have said, nothing new there. We're together there. It's nothing new. And so, for example, this is what we, for example, you have Fabry-Perot filters. They are special type of interference filters. So some people use that word interchangeably, but they work on the same principle. They work on the same principle, and therefore, I will not, so it's the same principle there. So we have talked about these are the optical filters, the interference filters, and because of that, you can choose your wavelength for your analysis if you have interference filters within an instrument. And that is made of a special dielectric material and that material is well known. Are we together there? So if you choose a particular material, then it's going to be to have given orders, given crystallographic planes, then you know for sure that it's going to, depending on the angle of radiation that you strike it, it's going to reflect light. And that is really, you have chosen the wavelength. So when you turn instruments, there are motors there. There will also be filters within the instrument, okay? So that's how we choose the wavelength, as we use that for our analysis. Let me talk about, remember once, what I've talked about is simply one wavelength of light, just one or two. But you can choose multiple wavelengths if you can vary you can vary the size of the dielectric material. So we have a special type of these materials, what we call interference wedges. If you vary that distance and the length, then you are choosing continually the wavelength. Does that make sense? So an interference wedge is a wedge dielectric of different thickness, can transmit a wide range of wavelengths without having to change the interference filter in an instrument. Remember, in an interference filter, if you have only one particular material with only one thickness, then you only can choose one wavelength, all right? So, but you can vary that thickness so as to choose various wavelengths. So you don't have to take the interference filters from your instruments. So the way around it is to choose an interference wedge. Okay, so then by choosing the correct position on the wedge, when light strikes that wedge, the variable bandwidths of about 20 nanometers can be isolated. That's, you can obtain that resolution within 20 nanometers. Okay. So I want you to be aware, think like, for example, somebody who is a manufacturer, or somebody who is saying, well, how can I make this instrument better? Then you choose materials that would reflect various wavelengths. So here, for example, is an example of an interference wedge. You can see from weak spaces, you can see this is where the diagram is. So you can see that distance there, 2D. Remember T. I go back to remind ourselves. Remember this diagram, the Fabry. T over cos theta, all right? So this is commonly used in optics. This equation is commonly used on optics, knowing that T is 2y, 2D. Are we together there? So then, normally then, you would see that this is out at T3, T2, T1, all right? Until you have 0 here. So that distance is varied, like a wedge. And if light can strike that particular position, there, or any other position, then it's reflected at different angles. That way, you have chosen various wavelengths. So again, we've gone through this. So now, there is something I want to emphasize here before I move on to the next part. I want to talk about the characteristics, the transmission characteristics of a typical filter. So it tells you that you can measure the characteristics of a typical filter with either percent transmitters and wavelength. You see, those are the characteristics that you take into account, and the bandwidth. So all those three characteristics are used to describe the characteristics of, they are used to describe a given filter. You can choose percent transmittance, effective bandwidth, and the wavelength of light that particular interference filter is capable of isolating. So you have here this particular these are the bandwidths at maybe between 590 and 511 from here to here. You can see the interference filters are very effective to about 80% transmission. That is angstroms here. The wavelength is expressed in angstroms. Then you have others. You see, we talk about half peak height. That's how you measure the effective bandwidth from our last class, remember? So the other one here, if you have an effective bandwidth of 45 angstroms, then you have here around between 5090 and 5110 angstroms. Angstroms is 10 to the minus 9. So if you want to convert it to nanometers, 10 to the minus 9.
I think it's 10 to the negative
10 to the negative 10, yes, that's right, you're right there. So if you want to convert it to nanometers, then you divide by 10, right? So it's important there, that's the correlation for those who want in nanometers there. And if you are talking about 549 nanometers, you are in the visible region, okay? So those can be used in the visible region. That's what you see. If you operate between 6215 and 6225, that is an interference filter of bandwidth 45, again, the effective bandwidth. Then you operate within here, then the percent transmittance decreases. You can see that, right? Then you can still operate within an effective narrower bandwidth. If you want that, then you can see also the effective bandwidth decreasing, then the percent transmittance decreases. So those are all used. You can imagine all these numbers are within the visible region. So it ranks itself to operating within the UV visible spectrometer. So they are used there, or you can use them in fluorescence. Are we all together so far? This is where these are used. And so we've talked about interference filters. We know how they operate. We know the characteristics we use, or the particular parameters that are used to describe the filters. Now, we have special type of filters, absorption filters. Absorption filters are made up of colored glass or dyes, or a dye. Normally, these absorption filters, so pay attention here, please, because sometimes a question, you might get a question on interference filters and the absorption filters. So notice here, the absorption filters are usually, they are colored, they are made from colored glass. And the way they make them, you have materials that can make the glass colored, or a dye. And then usually they have a broader bandwidth of between 50 to 100 nanometers. Now, again, I was looking at this today morning. Your textbook gives you a different number here again. I've adjusted that. The absorption filters have effective bandwidth that range from 30 to 250. You notice that number there? I don't want anybody to be confused with this number when you read your textbook. Does that make sense? So it tells you this is the broader bandwidth, and usually effective bandwidth can range from 30 to about 250 nanometers. Let's go with the textbook from 30 to 250 nanometers. So that is the absorption filters. They have that range, okay? And you will find this range in the other the other editions. Well, they have just amended. We're together there so far. So you will see that compare the absorption filters with colored glass with a broader bandwidth of about 50 to 100 nanometers versus the interference filters. We have the absorption filters, and we have the interference filters. You see the interference filters have a narrower bandwidth. So glass, for example, you may be aware when you are doing the UV experiment, I asked some of you as to why we are using quartz vis-a-vis glass. Did I ask any one of you that question? Yeah. And what was the answer?
Quartz doesn't interfere.
It absorbs up to around, it absorbs the UV light. Glass absorbs the UV light, whereas quartz is transparent in the UV region. So that's why we use quartz in the experiment to see the whole spectrum. So glass absorbs certain wavelengths while transmitting others. And there are types of these absorption filters. We have, you can measure them with their band pass, the band pass of between 50 to 100 nanometers. When you talk of a band pass, what do we exactly mean by a band pass? What's a band?
I guess in this instance, a band is just a band of light specific.
Oh, yes, that's what it is really. It's a band of light within that narrow region, right? So that's what it is. So when you hear of a band pass, it's a light passing through that particular band, that width. So then we have what we call the cutoff light. You know, I'm trying to get this information on absorption filters, what they are good for. So the absorption filters can be of various types. They can be cut off filters. I've emphasized that, cut off filters. Cut off filters mean they have a high pass, a high band pass, which simply means they pass high wavelengths. Cut-off filters of two types here, or various types. We have bandpass absorption filters. We have cut-off absorption filters. We are all together so far? And cut-off absorption filters, usually, they are termed as high-pass filters. They pass high wavelengths, and they block low wavelengths of light. Low wavelengths. So this type of filter will be used for, remember, and this is where, if you have handled fluorescence, it becomes important. If they can see what they filter, they block low wavelengths, right? And they allow high wavelengths to pass through. When we do fluorescence, we have two wavelengths of light. One will be the excitation, the other one will be the emission, all right? So you want to cut off, for example, you have to excite it, that's a lower wavelength, and then you emit it at a higher wavelength. So this the cutoff absorption filters or high pass filters are useful for fluorescence. They're very useful for fluorescence because since the excitation light is lower, the excitation light is low, it has a lower wavelength and should be blocked. Are we together there? So usually you excite it, let's say 270, and you don't want the same light to come back, then you step ahead. I usually use 10 nanometers. From 270, step ahead so that you don't capture the excited light. So that's where you use these cutoff filters or cutoff absorption filters. And so they are useful for fluorescence measurements because the excitation light is usually lower and should be blocked, and the emission is higher wavelength and should be collected. So they will block the lower wavelength. All right. So we have talked about the band pass filters and the high pass or cutoff filters. Now, here is the difference here. You notice this diagram here has information that might skip. Here are 3 types of filters. Here are 3 types of filters. And I want you to note the 3 types of filters. Notice them there. You have the absorption filter. Absorption filters have a broader effective bandwidth, around 50 nanometers. When you look at the interference filters, you notice the interference filters, the effective bandwidth. Can you see the effective bandwidth for interference filters? They are usually a little bit lower, unlike the absorption filters, which have a broader bandwidth. And what is the other difference that you see between the interference filter and an absorption filter? A higher percent transmitters than the absorption filter. The interference filters have a higher percent transmitters. Besides, you can see the effective bandwidth, as we have said, how we measure it. We measure it at half peak height, usually higher. And then the broadness of the absorption filters. I will not talk about the holographic notch filter, but I want you to note those 2 differences between the interference filter and the absorption filters. Any question as far as this is concerned? Any comment, any ideas on where you see this applicability when you handle instruments or you have seen something? You've been exposed to some instruments and, oh, this instrument must be using this type of filters. Any instrument you can think outside either the lab or any exposure you have on instrumentation. Let's move forward. This is what we've talked about the source. We have looked at, when we are talking about filters, what specifically were we concentrating on again? So we were looking at selecting a wavelength. Yes. Filters. We are selecting a wavelength. They are wavelength selectors. And you can also use prisms to select a wavelength. Here are 4 things that we use for selecting the wavelengths. We use filters, which we have talked about. We use prisms to select a wavelength of light. We also use gratings and monochromators. So these are things that we normally use to select wavelengths of light. So we have said wavelength selectors, they select wavelength or wavelength the range of light. And this selected wavelength of light is going to strike the detector. And we talked about this slide. So this is nothing new. We talked about it early on. Usually, wavelength selectors are often combined with a set of slits, holes that choose some light. So there are various types of wavelength selectors. All right. You have those which are based on filters. Those are very cheap. You can buy them and throw them away. Cheap colored glass based on prisms, which currently have limited applications, although previously people used to use a lot of prisms before, early on. All they are based on gratings. You see the word here is great stuff. What does that mean? So in this class, we want to lay emphasis on that, right? So those are things we need to know. We need to know about gratings and monochromators. That's important if you want to make sure that you understand that particular part. So prisms usually, they are widely used on scanning in selective devices, and often, usually prisms are made up of salts such as sodium chloride, fluorides, but they are very delicate. Prisms are very delicate, often subject to damage in humidity and wide heat ranges. They are not widely used today in spectroscopy. They are not widely used in spectroscopy equipment. They used to earlier on, but now we have got a little bit better. And so in our knowledge. So those are, you can use those prisms. I'm sure this was demonstrated to you early on. It's a prism that disperses light, right? Sure. Or when people do some experiments, if you don't have enough money, like in the high school setting, you can use prisms to disperse light. And then they are nice on the cover of a Pink Floyd album. What is that? Okay, right. They are nice on that. I just want people to thank you, Maria. I hate you. Okay. And so now let's talk about the great stuff. The monochromators, right? That's where I want to lay emphasis. Now I'll talk about the prisms later on, just to give us an overview. I've just made sure that we know. So monochromators usually are based on diffraction gratings or prisms. Monochromators, there are various parts. I'm going to give you, after I show you a picture, I want to give you the various parts, but here they are. They are based on diffraction gratings. A slit is used to select a particular wavelength coming off the grating at a particular angle. Usually you have two types of slits. You have the incoming slit and the outcoming slit. So here is a simplified diagram of a monochromator, very simplified. But once you understand this diagram here, then you will be able to know exactly how a monochromator works. Very simplified version. So you have here an entrance slit. You have an exit slit, obviously. So what you have here is the entrance slit allows some light that is going to go into, call it this box here, or into the instrument. And what you see is a mirror. This mirror is carefully, the diagram is carefully drawn. There is the term collimating mirror. What does the word collimate mean? Anyone who can look it up? What does collimate mean?
Make rays,
Go ahead. Go ahead.
make rays of light or particles accurately parallel.
Exactly. You see those two rays of light there? They are parallel, all right? That's the point. You have to use the collimating mirror. Collimating mirrors, notice these rays of light one striking one spot here, another one striking another spot, and then they are going to be made parallel to each other. So that's the function of a collimating mirror. Are we together so far? That's the function of a collimating mirror, to make the rays of light parallel. Once they are parallel, we come to this part here shaded in green, is actually at the heart of a monochromator. And that's what we call a diffraction grating. This diffraction grating, it has what we call glaces, like teeth, all right? There are surfaces on it that, depending on where the light strikes that surface, it's going to reflect light. And so you have the collimating mirror making, in this case, two rays of light parallel to one another, and then they are directed to these places here, and you can see they are going to be, they will be reflected onto the focusing mirror, and the focusing mirror then is different from the collimating mirror. The focusing mirror will focus the light to particular spots, to a certain spot there, and those particular radiation or wavelengths of light that can go through the slit, that's the light that will go through. So you have this exit slit is like a selector of the wavelength that is chosen as because of this series of mirrors. We have collimating mirror, and then the collimating mirror reflects light onto the diffraction grating. And then the diffraction grating, depending on the angle, it's going to reflect the light onto the focusing mirror. So let me say that the diffraction grating is not static, all right? It can move. Are we together? It can move. And if it moves, then you can imagine various wavelengths of light going to be chosen. So within an instrument, there are the monochromator, the grating is going to keep moving. That way you are scanning wavelengths. Does that make sense? So sometimes when you hear the instrument stand, there are several things that happen, but a diffraction grating is going to tilt. And as it tilts, you're scanning the wavelength of light. Okay? So this diagram here has all the essentials of a monochromator. It has an entrance slit, there's a collimating mirror, it has a diffraction grating, a focusing mirror, and an exit slit. The details now. Okay? So the grating monochromator, that is, it has a diffraction grating. Notice what it does. It scans a spectrum. It scans a spectrum, which means to scan a spectrum will mean you vary the wavelengths continuously. So you can imagine all the instruments that we have are going to have a monochromator. Am I right in making that conclusion? Unless you choose only one wavelength. But most instruments are going to have this monochromator. The materials of construction of the grating monochromator depends on the lambda, the wavelength range of interest. Depends on the wavelength of interest, materials that are used. And what are the components of a grating monochromator? We have talked about them, right? You can list them, right? What are the components again? An exit slit, an entrance slit, an exit slit. What else? Collimating mirror and a focusing mirror. Collimating lens or mirror optic, which gives the parallel beam. You can have the grating itself or a prism that can also act, but normally prisms, as we said, may not be used much these days. a grating or a prism, which is going to disperse light into separate wavelengths, and a focusing mirror or a focusing optic, which reforms the rectangular image usually. So these are the 4 parts. We have already said this. You have any question here? That's why we say this is great stuff. All right, great stuff, because we do a lot of spectroscopy here with monochromators. Yes, sir.
Should we also include the exit slit in the detector?
Yes.
Okay.
Yes, there it is. I'll put it up. The exit slit at the focal plane, because that's important. Without the exit slit, then you have not, the detector can't detect the wavelength. The exit slit at the focal plane of focusing the object is going to isolate the desired spectral band. So this morning we have talked about important information here, as you can see, a lot of important information. Now, what I want to do next is to show you this kind of monochromator, and I will start from here. You notice there on the top, on the top of my screen, what is that title there? Yes, those 2 people. We worked on it and gave us this type of monochromator. And it's not really difficult to see. And then we have a very simple one using prisms. So then the Zani-Turner monochromator, we'll talk about it on Wednesday. And then after I talk about it, then I move on to the next portion of this section. This chapter is long, you can see. All right. Okay. I think everyone got the lab report, all right? It was sent via email. Some was sent on Saturday, okay? Because they were sent on Saturday, and some of them, a few of them were sent on Sunday.
You mean the corrected ones?
Yeah, the corrected one.
Okay.
So now I want to make that announcement on the corrected. I took the page to write every detail that I expect on every section. Did you see that? So if you want to pay attention to that and follow it, then you should be able to do the labs very well. Of course, you have to take care of the language and so forth, but that's my expectation. Those are the things that I look for throughout the labs. Okay, yes, ma'am.
I know we talked about it, about removing the June Mondays.
Let me announce here, Monday seems to be a better time so that you can turn in your labs on Monday rather than Fridays. I think it works better even for me and for everyone, because, yeah. And we'll meet this afternoon.